Okay, so thank you, Philip, and for your very kind introduction. So I'm so happy, to meet so many old friend like Emmanuel and Ignacio and also Gerhard. But I'm so sorry for this time I could not visit in person. And due to, my single visit to Europe is only for 5 days, so I have to come back to China. So try to visit you next time. So, first of all, dear friend and colleague, I would like to thank you for the kind arrangement and which allow me to make online presentation. And in the following, I will, present a brief introduction on our work, which have been done in our group in the field of quantum information processing and with photon and atom. So as we all know, three pioneers, Alan Archipel and John Clauser and Anton Zilling, won the Nobel Prize in Physics 2022. And this is very inspiring and for the whole quantum community. So, and the prize mainly and recognize their incremental contribution with entangled photon, which established the violation of Bell inequality and pioneering quantum information science. So we know, so the violation of Bell inequality immediately implies the quantum world is somehow intrinsically random. And this is because for entangled state, before the measurement, even the God does not know which measurement result and will be. So an immediate application of quantum entanglement is in the so-called device-dependent quantum random number generation, by which true random number via violation of Bell inequality can be generated and even with suspected devices. So the device-independent quantum random number generator, which is secure against both classical and quantum adversary, was first reported by us in 2018. So the DI quantum random generation could find various applications in numerical modeling, artificial intelligence, and quantum cryptography, and so on. So another interesting application of Bell theorem is the so-called entanglement-assisted secure communication as proposed by Arthur Eckhart in 1991. So in this scheme, the perfect correlation of entanglement can be used to share a secret key between Alice and Bob. In the absence of eavesdropping, the entanglement will not disturb it, so the maximum value of S can reach 2 square root 2. But if there is eavesdropping, so then the unauthorized measurement will leave the state of the photon and identified, so the value of S cannot exceed 2. So in 2022, device-independent QKD quantum key distribution certified by Bell theorem were demonstrated independently by three groups, including us and Howard Winford group at MPQ, and also a group from University Oxford. However, the secure distance and the key rate of these three DRQK experiments are really very short, and the key rate are much limited, so it is still far away from any practical application. So of course, interestingly, besides discovery in quantum foundation, so from the test of quantum non-locality, quantum physicists have developed groundbreaking technology for coherent manipulation of quantum system, and this consequently lead to emerging quantum information science, including quantum communication, quantum computation, and quantum simulation, and quantum metrology, and so on. So as we all know, quantum key distribution is the best known quantum communication protocol. For example, one could exploit the single photon based B84 protocol to implement quantum key distribution. Then with the help of the shared secret key and one-time pad inclusion, one can achieve the unhackable or unconditional secure communication. And also, as I just mentioned, one can also follow Eckhart 91 protocol to implement entanglement-based quantum key distribution. So quantum teleportation is another interesting application of quantum communication and a way to transfer quantum information from one particle to another without sending the particle itself. So, and although nowadays it's far, far away from teleporting a complex object, it is possible to teleport various quantum states in the network, which is essential ingredient for distributed quantum information processing. So interestingly, the state of one particle of entangled state can also be teleported. For example, for two entangled pair, 4 and 1, 2 and 3, if one perform a Bell's measurement on particle 1 and 2, then the remote particle 4 and 3 that never interacted can be entangled. So this process is called as entangled swapping, which, as I will show you, plays an essential role in quantum repeater protocol. So as we already know, the first proof of principle concept demonstration of QKD and teleportation were done in 92 and 97. So we can see from here, then the distance are quite shorter, both on about 30 centimeters. So actually, with various experimental efforts, by 2005, several groups have demonstrated quantum key distribution over 100-kilometer fiber. However, it was soon found that due to the imperfection of realistic quantum device, mainly due to the imperfect single photon source and imperfect single photon detector, there are several serious circular loopholes in all private experiments, making the secure distance and was limited to the order of 10 kilometers. Therefore, and there are two major challenges toward large-scale quantum communication before we can finally promote any practical application. So first, we need to overcome the circular loophole caused by the imperfection of realistic device, mainly due to, as I just mentioned, during the imperfect single photon source and imperfect single photon detector. Second, and we need to overcome exponential photon loss in fiber to extend the communication distance. For example, in 1,000-kilometer commercial fiber, and even with a perfect 10 gigahertz single photon source and ideal single photon detector, without quantum repeater, only 0.3 photon can be transmitted on average per century. So we have to solve these two problems. One is security problem, one is to extend the communication distance. So to solve the security loophole caused by non-ideal single photon source, in 2005, and two independent groups proposed the so-called decoy state QKD, by which one can achieve secure QKD with non-ideal single photon source. So in 2007, and two independent teams, including us, and we implement decoy state quantum key distribution over 100-kilometer fiber. So in 2003, and following the original and the protocol as suggested by Haoquan Lu, the so-called measurement device independent QKD, which is immune to any attack on detection, then and we demonstrate MDI QKD to close the loophole caused by imperfect single photon detector. Very recently, by exploring and those advanced technology in frequency quant, and also the time dissemination method, and the so-called the twin beam MDI QKD in field fiber has been extended to a distance of 500 kilometers, and in laboratory, and this distance has been extended to 1,000 kilometers. So as pointed out by Charles Burnett, in MDI QKD, so if the untrusted device remains outside Alice's and Bob's trusted enclosure. So they need only trust themselves not to have inadvertently create a side channel to Eve through the incompetent design of their do-it-yourself light source. So by combining MDR-QKD and do-it-yourself light source, so the information theoretically secure QKD with a related device can be approached properly already. So besides those excited or solid advance in 5-bit QKD and textual quantum teleportation, one may further ask how to extend the quantum communication distance further. So one possible solution, we count back to almost 30 years ago, as proposed by Hans Briegel and Wolfgang Duhl and also Ignaz Reich and Peter Zoller. So the so-called BDCZ scheme. So one possible solution for large-scale quantum communication is a quantum repeater. So the central idea of quantum repeater is to solve the photon loss problem via entanglement swapping, and to solve the coherent problem via entanglement purification. So entanglement purification is a way to distill a subset of highly entangled state from a larger set of less entangled state. So experimentally, it would impose 3 major requirements. So entangled swapping with high precision, entanglement purification with high precision, and quantum memory with high performance. So I still clearly remember, I think it's during the East of 2000. So Anton Zeilinger came to me and he said during the conference, he heard Ignaz Reich mention, so the purification at that time is one of the most important topics in quantum communication. Then we start to think about how to achieve high precision entanglement swapping and purification. So the first entanglement swapping experiment was done in 1998. So late in 2003, we implement a high precision fault tolerant swapping experiments and via high precision 4-photon interferometer. But the realization of entanglement purification turns out to be a little more difficult. Because the original purification scheme, we would need a CNOT operation between two independent photons. But we know, the photons, so the photon-photon coupling is very weak, so it's very difficult to achieve, a CNOT operation. So therefore, and in 2001, and we proposed a practical scheme for entanglement purification only with linear optics, by which the required nonlinear additive between two individual photons can be induced by post-selection. So following this scheme, and in 2003, and we managed to experimentally demonstrate the high precision entanglement purification. Now the only missing element is so-called quantum memory. So the reason why we need quantum memory is, without quantum memory, then the cost of result in multi-stage realization of entanglement swapping is proportional to 1 over p to the power of 2n. So where p is the probability of emitting an entangled photon pair in a specific experimental run, such a scheme is not scalable. However, if we know, when entangled pair is created and can store them on demand, then the total cost of implementing entanglement purification and entanglement swapping is proportional to 1 over p squared. So in this way, we can achieve efficient entanglement distribution of quantum entanglement between distant locations. So in 2001, and Lu Minduan and Michael Lukin, and also Ignaz Reich, and also Peter Zoller, they proposed the so-called DLCZ, single photon quantum repeater scheme. So at that time, experimental realization over long distance of DLCZ scheme is very difficult. because the single photon interference and would require a stability and the single photon wave packet on the order of 100 nanometer. At that time, it was very difficult. Although now, with the help of frequency con, and we can solve this problem. So therefore, and a few years later, we propose an alternative scheme, which is very much the same as the BDC scheme. And in BDC scheme, only need 2 photon interference, then and stability is much less, which is only about a few tenths centimeter. So 1 year later, we experimentally realized a robust quantum repeater scheme, which only requires stability a few tenths centimeter. So by making use of 2 laser-cooled atomic ensemble, which are connected by a 300-meter fiber. So from here, you see how I gradually, transition from pure photonation to and also atom optician. Yes. However, so the first experiment at that time, so the lifetime and the efficiency and is very bad. So actually, in order to enable long-distance quantum repeater, so the storage time must be long enough to ensure an every node can create an entangled pair. Moreover, and the stored quantum state must be converted back to photonic excitation with a sufficient high efficiency to establish remote entanglement. So from this figure, you can see in our 2008 experiments, so the coefficient of our quantum memory is very bad. So from here, you can see, the lifetime has to be improved by 8 order of magnitude in order to meet the requirement of 500 kilometer quantum repeater. So since then, and many technology development has been carried out, including employ clock state, which is insensitive to magnetic field, and using a ring cavity to increase the retrieval efficiency, and using a 3-dimensional optical lattices to confine the position of each atom. So by 2016, and we finally managed to prolong the lifetime to this point. So in principle, and the new coefficient already support quantum repeater enabling quantum communication at a distance of 500 kilometers. However, we still have more difficult that we need to solve. And for example, and to connect, just a second. So to connect a quantum memory node over long distance with fiber, we need to shift the atomic wavelength to telecom wavelengths. So after a few years effort, we managed to convert the atomic wavelength, which is about 800 nanometer, to telecom wavelengths. So in this way, and we successfully achieve quantum entanglement between remote quantum memory over tens of kilometers. So very recently, and last years, in experiments, we managed to achieve the first multi-node entangled-based quantum network over a metropolitan area. However, a practical quantum repeater at the 1,000 kilometer scale might still need 10 more years. So our plan is, I will mention, later, is to achieve, deterministic entanglement distribution with the help of quantum repeater to achieve, deterministic entanglement distribution over 1,000 kilometer in next 4 to 5 years. That's what we are doing now. So as I just mentioned, although since 1998, we already start to perform the first entanglement swapping experiments, but now we're still not able to show the advantage of quantum repeater. So back to 2002, in the parallel development, we start to think about another promising solution for global scale quantum key distribution, which is through satellite in space. The satellite to the ground connection has significantly reduced the photon loss, since as the effective thickness of from satellite to the ground station is only about 10 kilometer horizontal atmosphere. So most of the photon can pass through the atmosphere. Therefore, since 2003, we have spent more than a decade to develop the key technology for low orbital satellite-based quantum communication by performing a systematic ground test. So in all former experiments, we managed to verify quantum state can pass through allosphere. We can overcome the high loss in the satellite to ground channel, and also we can manage to overcome all the demand condition for the low orbital ground to satellite quantum communication. So with all this effort, and in 2016, and we launched the first quantum satellite missiles in Jiuquan Quantum Satellite Center, in Jiuquan Satellite Center. So with the missile satellite, we achieved QKD and between satellite and ground station at 1,000-kilometer scale. In the first experiment, and the observed key rate and is about 1 kilohertz, which is about 20 order in the sense of transmission efficiency, which is about 20 order of magnitude higher than using the same fiber and over the same length. So we also achieve satellite-based entanglement distribution and quantum teleportation from ground to satellite and so on. So then, through an international collaboration in 2018, and we managed to use a quantum satellite as a trust relay to perform intercontinental QKD and with Beijing and Vienna. And so now we also in collaboration with our colleague from Italy and India and South Africa, and also colleague from Canada in Calgary, and to jointly explore the visibility of global quantum communication. So interestingly, along with the quantum communication experiment, many technology for coherently manipulating photon has been developed, such as high precision quantum interference of independent photon and ultra precise phase stabilization, single photon detection, and precise frequency and timing dissemination and method. All these technologies together already enable optical information processing, including quantum computation. So, and given the huge technological challenge, and it will take quite a while before one can really realize a fully functional quantum computer. So to ensure a healthy development of quantum computation research, the scientific community has set a three-stage goal toward the ultimate realization of a practical quantum computer. So the first one, or the milestone one, is called quantum computational advantage. So, and which means the speed up is so overwhelmingly huge, so no classical computer can perform the same task in a reasonable amount of time, and is unlikely overturning by classical algorithm or hardware improvement. So the second one is to construct a quantum simulator to efficiently mimic the evolution of a complex system, quantum system, for the studying of the mechanism of high TC and so on. So the third and the final goal is a long-term goal, is to achieve universal and programmable quantum computation with the help of quantum error correction. So one may ask why quantum computation advantage is important, because to me, and quantum computational advantage could show the essential difference between classical and quantum physics. As in, just like using the Bell theorem to refute Einstein's local reason, establishing quantum computation advantage by using entanglement as a valuable resource, we could refute the so-called Church-Turing thesis, which states classical computer can simulate computational power of any physical process with polynomial overhead. But actually now we know it's not possible, especially for quantum process, for complex quantum process. So in 2019, and Google first announced the quantum computational advantage with 53 superconducting qubit, the so-called Sycamore quantum processor. In the experiments, the Sycamore generated a million noisy sample in 200 seconds. And at that time, and they claim, which would take a classical supercomputer 10,000 years. However, recent study already shown, and with the help of the so-called tensor network algorithm, which is also inspired by quantum entanglement. So the same task can be completed by a classic computer in 14 seconds. And furthermore, if we have unlimited memory, so the classic computer running time would only need 1 second. So we know, so originally advantage announced by Google in 2019 and has been overturned. So and because we are, started a little bit later, and we are somewhat a follower, to the Google's, an approach. So, and 1 year later, and we realized 66 qubit superconducting quantum processor, we call it Zhu number 2, and which relies a strong quantum computational advantage, via random circuit sampling. So later on, and Google upgrade Sycamore system to 70 qubit. And according to their published result in 2024, and the advantage ratio now compared to the achieved classic algorithm is 9 order of magnitude. But suppose if we are allowed to use unlimited memory, then advantage ratio of the Sycamore, upgrade Sycamore compared to classic computer is 3 order of magnitude. So almost in a simultaneous development, of course, we publish our result 2 months later, and in our 105 qubit Zhu number 3, and our advantage ratio has been and improved by 6 order or 3 order of magnitude respectively. And also beside our activity in superconducting quantum computation, and we in the parallel system in 2020, and we use photon to realize the Gaussian boson sampling machine, Jian, which shows strong quantum computation advantage. So in our first Jian experiment, we detect up to 76 photons, and its sampling rate is about 5 order times faster than the classic computer with the currently known best algorithm. So very recently, so the Jian number 4, and we already managed to observe 3,000 to detect 3,000 photons. So, and we are now performing the data analysis. So the expected advantage ratio compared to classical supercomputer is about 40 order of magnitude. So in this sense, we could claim and the quantum computation advantage already be well established. But the bad thing is such algorithm do not find too many practical application. So therefore, a really useful and universal, fault-tolerant quantum computer is still far away. So fortunately, and the quantum simulation may already lead important application in the near term. So very recently, and we use our superconducting system to explore the bottom-up approach to observe the first fractional quantum Hall effect using interacting photon. Yes. So and this idea is very much triggered by Emmanuel's paper many years ago, and he tried to show some sort of four-body interaction and so on. So and which is a quite similar method. So our method is that, and we design and fabricate a new superconducting resonate. We call it is plasmonium, and such that only one microphoton can be confined in the resonate. So, but it will block a second photon to jump in. This is very much analog to the Coulomb and repulsion. So next, to mimic a strong magnetic field, which is traditionally required for the fractional quantum Hall state, and we use precisely and controlled AC and microwave to couple adjunct box. This creates an artificial gauge field. So this is also triggered by our cold atom experiment engage and field simulation I will mention and later. Then so the photon will hopping through, and so the photon will hopping through in these lattices will accumulate a Barry phase, much like the motion of the charged particle in a magnetic field. We then arrange this photon box into a 4x4. You can see into a 4x4 and a box. So in this way, so the entire system is highly controllable with ability of to address individual site and program the photon interaction and providing a new avenue for experimental observation and manipulation. So currently, we are working on this system. We want to see the possibility whether we can explore such system to observe the non-abelian fractional statistics. That's one activity we're going on in our superconducting system. And then in this experiment, we further prepare the target and a fractional quantum Hall state. This was achieved through a process called adiabatic and preparation, where we carefully involve the system from a simple initial state of localized photon into a more complex and correlated fractional quantum Hall state by gradually increase the coupling strength and tuning all sides to resonance. So once prepared and we characterize its property, and we observe we observe the hallmark channel flow of this photonic state. They move in a specific direction along the edge. Okay, and we even see inverse current pattern in the bulk of system. So the radial current are appreciably suppressed. So next, we probe for two defining characteristic of a fractional quantum Hall state. So the first one is the incompressibility. Imagine try to squeeze in a liquid, it resisted. Similarly, our fractional quantum Hall state, photon state, resisted changes in density when a weak local potential is applied. So the second and perhaps most definitive test is measuring the Hall conductivity. We found that the Hall conductivity is quantized and it's quantized at a value very close to 1/2, precisely what we really expected for this particular fractional quantum Hall state. And here I would like to mention some similar result has also been demonstrated with ultracold atom system. So and from our colleague from United States. Of course, I think the superconducting system, due to the advantage of engineering, an advantage. So probably we can go a little bit fast and so on. So now, I come to the last part of my talk. And because one of our focus is still on the quantum simulation with ultracold atom, I can still really remember in 2000, actually in 2006, and Emmanuel invited me to visit him. And so from that time, we decided, okay, that's something, and we should really go. So compared to other quantum systems, Ultracold atoms have several specific advantages, as we all know, for quantum simulation. Since the state and the interaction of the atom can be precisely controlled with many advanced methods, such as the Raman technique and the Fishbach and resonance and optical and lattices and so on. Such various Hamiltonian can be implemented artificially. So in particular, Emmanuel and Bloch achieved the first quantum simulation with Ultracold atom in optical lattices, and which not only opened the door of quantum simulation with Ultracold atom, but also and greatly inspired a series of work in this field. So here I will only mention one of our most recent development using Ultracold and Fermi atom. So in our leasing experiments, and we conduct a series of quantum simulations of strong correlated many-body system. So first, we study the macroscopic property of strong correlated system. So in our system is lithium. So where the transport property are of fundamental interest. So according to the Landau's two fluidity theory, two types of sound wave and predicate transport phenomenon are expected to exist in superfluidity. So the first sound, which is density wave-like, and which density wave like ordinary sound, and the second is a temperature wave, and which is unique to superfluidities. So at the finite temperature, so the coexistence of the normal and superfluid component lead to sound attenuation. So this attenuation arises from two mechanisms. So and viscous damping relate to the diffusion and momentum diffusion, and characterized by the shear and viscosity eta, and also bulk and viscosity theta, and the thermal damping and relate to the heating diffusion, and characterized by thermal conductivity kappa. So therefore, by studying and the property of sound wave in Fermi superfluidity, we can access the key transport coefficient. So to achieve this goal, we would need a really nice homogeneous superfluidity. So in our experiments, and we define and we develop techniques to prepare a homogeneous Fermi superfluidity in a box trap with Fermi energy gap up to 50,000 and up to 50,000 and kilohertz, and precise temperature control. In parallel, we also develop the Bragg spectroscopy method with lower momentum transfer, which is about 5% of the Fermi momentum, and with a high energy resolution. This enables us to perform high precision measurement of the systems high precision measurement of the system density response spectrum. So building on this, we systematically measure the density and response of unitary Fermi superfluidity, and observe and clear signature of both first and the second zone. So the experimental result show excellent agreement with the theoretical and prediction based on dissipative two-fluid hydrodynamics. So from this measurement, and we extract the key transport coefficient, including thermal conductivity and viscosity. And we also found the transport coefficient of the unitary Fermi superfluidity approach universal quantum limit. So for example, and the thermal conductivity and skill as and NH bar and KB and over M, which is determined solely by the reduced Planck constant H bar and the Boltzmann constant KB and the particle mass M and density N. So moreover, we also observe and the lambda peak of the and the lambda peak and of the thermal conductivity near the superfluidity transition, revealing the presence of a large critical region in a unitary Fermi gas. So then, in the second experiment, and we start to, consider to address the microscopic nature of strong quality system. So as we all know, according to the BCS and the theory, Fermi pairing condensation and the emergence of the superconducting energy gap all occur simultaneously simultaneously at the phase transition temperature Tc. So this leads to a fundamental question. So can fermion form Cooper pair above Tc and leads to a significant pairing energy gap? If a pseudo gap is observed in unitary Fermi gas, it must originated from many body pairing above Tc. So, and we know, and in 2010, Jian and his colleague measures the spectral function of the normal state of strong interacting and Fermi gas. However, they did not measure or they did not observe the two branch of the quasi-particle and the suppression of the spectral density near the Fermi surface. So moreover, so the theoretic study suggests that the experimental data could be fully described using Fermi liquid theory. So therefore, we still have to remain a main challenge in this pioneering experiment. So the first one is the harmonic trapping potential leads to a non-uniform density distribution of atom, result in a density-dependent ratio frequency spectrum and response. So second, so the final state atom used in the spectroscopy still interact with the atom in the initial many-body system, causing broadening and shifting of the single particle spectrum. So to address these two difficulties, and we propose to measure the single particle and the spectrum of a homogeneous unitary Fermi gas. In order to achieve this goal, we develop a momentum-resolved microwave and spectroscopy without serious final step and state effect. Yeah. So using this method, we systematically and measure the single particle spectrum function of a homogeneous unitary Fermi gas at various temperature. So as shown in this figure, yeah, as shown in this figure, we observe two quasi-particle branch resulting from the presence of energy gap. And more importantly, and even above the superfluidity transition temperature, or in other words, in the normal phase, we still clearly see a suppression of the spectral weight near the Fermi surface. This, is the smoking gun evidence for the pairing pseudo gap. So before concluding my talk, I will briefly mention our newest result in antiferromagnetic phase transition in 3D system. So the fermionic and Hubbard model is a fundamental model that describes strong correlated electron behavior in the lattice. However, both theoretical and numerical study are extremely challenging. So for the lower temperature phase diagram of the Hubbard model, theoretical study can only affirm can only establish the ground state at half filling as an antiferromagnetic phase, which has not yet been experimentally observed before. Moreover, the state of doped system can no longer be accurately simulated even using even using supercomputer. So fortunately, using Ultracold Fermi atom in optical lattices, we can create a clean, Fermi-Hubbard quantum simulation system, which provide a possible promising approach to solve the model. So the first step is to construct a quantum simulator capable of verifying the antiferromagnetic phase transition. So, and with the former development technology, and by combining a box, a trap potential, and with the flat top optical lattices, we achieve the adiabatic preparation of spatially uniform fermionic Hubbard model. So the system consists of about 800,000 lattice size with a homogeneous Hamiltonian parameters and the temperature well below the Neo temperature. Building upon this platform, and we develop a spin-sensitive and Bragg diffraction and scattering technique by precisely tuning the interaction strength, temperature, and doping level, and we directly observe definitive evidence of the antiferromagnetic phase transition, a power law critical divergence of the spin structure factor near the phase transition. This marks the first experimental verification of the antiferromagnetic transition in the Fermi-Hubbard model. More importantly, and the observed antiferromagnetic magnetic transition and doping is already beyond the current ability of classical calculation. So it clearly show and the advantage of quantum simulation. Yeah. So currently, and we are working on a new experiment to observe the single band superfluidity with attractive interaction. So we hope we will manage very soon. So here I will just briefly mention, we also, triggered by Emmanuel's theoretical work. Then we also, have demonstrated parallel generation of atomic entanglement in optical lattices and showing the toric Hamiltonian and the analytic fraction and fractional statistics. And very recently, in collaboration with Philip Hock at the University of Trento, and also Yad and Halmish, who is also in University and München and other colleagues, we managed to explore such a system, for studying lattice gauge theory in collaboration with many our colleagues. So also probably you already know, we also have some related work in the quantum simulation with the Gauge potential with the neutral atom and the quantum simulation of Ultracold and the chemistry and with molecule. So I think maybe in the future, we hope we can manipulate more than 10,000 atoms to study scalable multi-party entanglement and autocorrection, by which one can mimic strongly correlated topological matter phase diagram of phi and a Fermi-Hubbard model, and so on. So to conclude my talk, I would like to briefly mention, some future prospect. So in the future, it is foreseen to establish a global quantum network by combining metropolitan quantum communication network and intercity quantum communication connected by quantum repeater. So the quantum repeater will really play a significant role, I think, and within 10 years, for which I'm quite confident. So, and we're really on the, and halfway. And this area could be very optimistic. So as to the satellite-based quantum communication, there are still several technological challenges need to be overcome. So for example, as a low orbital satellite like MCQST, and which cannot cover the whole Earth directly, and can only work in Earth's shadow. So the solution is to form a quantum constellation with multi-low orbital satellite to build a more efficient network. So in next year, we are going to launch 4 microsatellites to form a quantum constellation. Moreover, we are also working on the development of a GEO satellite, and which is scheduled to be launched around 2027. So with the help of the GEO quantum satellite, and we should be able to perform entanglement distribution on 2 different continental over distance of 10,000 kilometers. Yeah, so that's something and what we are working on. So interestingly, and with the help of with the help of large-scale quantum communication network, we can also provide a new platform for the study of high-precision quantum metrology. For example, very recently, we're exploring we are exploiting the long-distance quantum teleportation protocol to establish a quantum enhanced telescope area. For example, now the best single photon interference a telescope, the baseline is only about 100 meters. So currently we are working on test experiments. We want to see the possibility to build up a quantum enhanced telescope area assisted by quantum teleportation. So in this way, one can enormously increase the angular resolution of a telescope area. So for our GEO satellite, we will also carry on ultra-precise optic clock with a fractional stability 10 to minus 19, and by which we can provide precise time information sharing with a much long time instability, which is a 4 order of magnitude better than the micro time sharing. So in this way, we can provide a new method for the new definition of the time unit second. So very recently, we already have some preliminary result, and which show the possibility to perform intercontinental time frequency dissemination. Okay, so in long run, with the help of the optical lattice atomic clock, it will be possible to even achieve a ultra-precise optic clock with a fraction instability up to 10 to minus 21. So in this way, one can use this method for the detection of gravitational wave signal with lower frequency to 0.1 hertz, and which is a very compensation to the LIGO and to the LISA and experiments. Yeah. So all my aforementioned activity can be found in my and our recent review. Then finally, so in our next, okay, my time is over. So in next 5 years, I think it will be a very fruitful time for coherent manipulation of a few hundred or to a few thousands qubit of atom or superconducting qubit, by which one can really investigating the mechanism of high TC, quantum Hall effect, and so on. So in long run, maybe in next 10 to 15 years, or probably even a little bit longer, I think it should be possible and to achieve coherent manipulation of millions of qubits, which may lay the foundation for universal quantum computation with the help of quantum error correction. So thank you for your attention.
Yeah, great. Okay, thanks a lot for the very nice talk and the overview of all these activities. I'm sure there are many questions. I think we have a lot of people in the room, so perhaps just raise your virtual hand on Zoom if you would like to ask a question, so we keep the overview. Then, yeah, let me start perhaps. So, you showed this vision of the sort of really like large scale quantum key distribution with the local like fiber networks and the long range satellite networks. So, how do I imagine? What is there to say about say key rates in such a system? So, is that always limited by the key rates via the satellites, or basically.
So for the satellite, which very much depend on the weather. So now for our resonant microsatellite in each orbiter, we can generate more than millions of key, and which is the final key. So then that means we can really, finish the key distribution process in the single pass. Then also we have optical communication, but not quantum communication. We have optical communication terminal, which can help us already finish the information transfer, which is really online. Information transfer. So, and which is quite good. But of course, and because if you do not want to have unconditional security, then combined with some traditional asymmetry asymmetry encryption method. For example, the ASE, then you only need to have 252 or something like that, which are sufficient to send one package of large information. So which already could be quite useful. So for our high orbital satellite, so the point-to-point annual key distribution rate could up to 1 to 10 gigabit. Which is quite big. Quite a lot.
Okay. And the log networks, so those really rely on atomic repeaters, like on the atomic ensemble repeaters, or what's your vision there?
So you mean for the satellite? No.
No, for the fiber networks?
Yeah, for the fiber network, I think without quantum repeater, then few hundred kilometers will be really the limit. Probably 200 or 300, because then the key rate will be extremely lower. But I think because although people start to working on quantum repeater for many years, now gradually we really see the dawn. Now we really will have a very fast development. I'm quite optimistic.
Okay, great. I see a question from Gerd Rempe.
Yeah, first, let me see. Yeah, I'm on.
Hi,
thank you. Hi, Jian Wei. First of all, thank you very much for this wonderful talk with a firework of results. It's really enormous. Wow. I have a question to you as maybe someone who has experience with different platforms like photons and atoms and superconductors, etc. How would you compare the different approaches for quantum computation? Doing quantum computation with photons, or doing quantum computation more with atoms or Rydberg atoms or superconductors? What is your general attitude to this in terms of maybe what are the possibilities, or what are the challenges, or what do you think is more promising, or what can you say about this as so broadly oriented person?
You're right. So now in China, because we have quite several groups who are working on different systems. So I think it's far too early to conclude which one is the best. But for the time being, I think as superconducting qubit is still the most advanced, because now as I just mentioned, we already have a few hundred really functional qubit. But then very soon we will test 1,000 or 3,000 physical qubit. So if the error correction goes all right, and which will very much depend on the logic gate precision. If we can achieve 99.7, then for the surface code we will only need a few hundred qubit physical qubit to encode one logic qubit to protect the decoherence. Okay. But if we only have 99.5, then we would need almost 1,000 physical qubit to protect the one a logic qubit. So it seems quite difficult. So in this thing, our main focus is try to improve the logic gate precision only a little bit. Then we already give us enormous gain. So that's one thing. So the second thing is for the superconducting system, if we want to really scale up to millions qubit, then our refrigerate, so the cooling power is not enough. So we are working hardly to develop our homemade high cooling power refrigerate, which could be useful for at least 10,000 superconducting qubit. And also for the electronics, it becomes much more complicated if you take the traditional way. So we need to find low temperature CMOS electronics and SFQ to see whether we have some, integrated electronics can be employed in the superconducting qubit. So that's the strength and also the weakness of the superconducting qubit. And for the neutral atom, we also have some, and good result recently. But the thing is, for the neutral atom, you really need to have a very high power of laser system, and which maybe if we go up to, a few 10,000 neutral atom, now the laser system, we cannot find such a laser system on market. So we're also developing the higher power laser system, but with very lower noise. So these two systems, to me, at the present, are the most advanced one. But of course, also ion trap and so on. but I still would give great expectation to the photonic stuff. So as long as we can manage to achieve strong coupling between individual photons, then, I think photon will be the best candidate. But now we are working hardly try to achieve the high coupling, strong coupling between individual photons. We work this for very long, but still not too much progress. Yeah.
And why do you think it's the best candidate? Is it because you don't need low temperatures? Everything can be done at room temperatures?
Okay.
Because the disadvantage with photons in some sense is that they get lost, no? And
exactly.
Superconductors don't get lost and atoms don't get lost.
In order against the photon loss, so the loss correction code is much more simpler than the error correction code. Because in photon, the main error is from the photon loss. And we can also explore the very simple, loss correction code, which is much simpler compared to the other system, because the other system has a strong coupling with the environment. So the coherence is a huge matter. So it's a huge problem. But for the photon, as long as you have a high quality interaction, if you really can manage to have the deterministic CNOT operation, then for them in your cavity parallel, if you manage, then I think this would be the best solution. Because now with a single photon detection, we could already have a very high single photon detector. So yeah, so we're still working on this.
Yeah, I agree. Thank you very much.
Okay. Thank you.
And so what do you have in mind when you speak of this strong coupling between photons? Are you thinking of like atoms and cavities, or can you say what approaches you're following?
So it means as interacting photon, and you mean? Yes. So for interacting photon in the and the superconducting resonate, I think is mainly could be good for the for the topological quantum computation. Yeah, because we have a very clear load map. So maybe we will be probably our traditional quantum optician. We will much faster than the condensed matter quantum physicist. I will see. We have plan. We hope to show the non-abelian statistics within 2 years or 1 or 2 years. Yeah.
So you were talking about microwave photons just now.
Yeah. Yes, microwave photon. Right. Okay.
Other questions from the audience? So I'm of course also interested in the cold atom work that you showed on the superfluid and the Fermi-Hubbard quantum simulation. So one challenge in all of these experiments is always like the temperatures, the residual temperatures that you have in the lattice, right? And Marcus Greiner demonstrated these like very nice new cooling methods. Do you have thoughts on how to do this in, say, for your 3D experiments, or like are you working on new ideas there on how to reach lower temperatures?
Yeah, so I mean, in order to measure temperature, I mean, actually, and before we install and the cold atom cloud into our lattices, so temperature is about 0.2 and TF, so and Fermi temperature. But then when we install the atom into the orbital lattices, it's not possible to measure temperature. But then we try to switch off our orbital lattices. Then we try to measure and temperature again. Then we have probably something like 30% of increase of the temperature. Yeah. But now, I mean, more or less, I mean, we think, I mean, such temperature is already enough to see the a single band superfluidity and with attractive interaction. Yeah. So, but of course, we work for a very long time to make the homogeneous and trap. So this is somehow, yeah, it takes quite some time. Yeah.
Yeah, there's also an achievement. I mean, to deal with the mass transport and so on is always difficult.
Yeah. Okay.
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 I don't see any more questions right now. So,
okay,
yeah.
wonderful.
Okay, then I would say thanks a lot again for joining us online and for sharing all these results. Congratulations.
We hope to see you soon.
Yeah, see you in person.
So thank you,
next
Philip.
time.
Yeah. Thank you very much.
Great
so
to
all
have
the
you.
best.
Thanks.
Bye-bye.
Okay, bye-bye. Thank you.
Thank you also, Philip. Then I will stop the recording now. Thanks. Cheers.
Okay, great. Yeah. Thank you for organizing.
Yeah, you too. Hope to see you next week.